Okay, so the squeeze theorem tells that if h of x is less than or equal to f of x, which is less than or equal to g of x. So this says that f of x is between h and g for all x in an open interval for some period of x. Okay, so in this picture over here, we have g is on the top and h is on the bottom, and f is between those two functions the whole time, at least for this interval that we're focusing on. And if that's true, and then if you know that the limit on the one end and the limit on the other end both equal the same value L, so in this picture here, these functions as x approaches c approach the same value L here. Then if that function is squeezed in between it, then that limit also must equal L. We're going to use the squeeze theorem here to prove one of these theorems, one of these special trig limits here. So what we're going to do is we're going to prove that the limit as x approaches 0 of sine of x is equal to 1. Okay, if you try direct substitution with this limit right here, then you're going to get 0 over 0, which is an indeterminate form, but we can't do anything with that limit. Okay, so we're going to prove that that is equal to 1 using the squeeze theorem. So if we take this this inequality right here at the bottom, which this area here above it is proving that this inequality is true. So we're going to take this to be true, okay? So this inequality is true, and we're going to use this inequality. So a lot of times with the squeeze theorem, you either start with an inequality where you know one function is bound between two functions, or you'll have to create one yourself. So here we're going to start with our own. And we want to show that the limit as x approaches 0 of sine of x over x is equal to 1. That's the goal, which was the limit above there. So if we start with this inequality here, and then if we take the limit as x approaches 0 of cosine of x, so the function on this end, and the limit as x approaches 0 of 1, which is this one on this end, and if these both are the same value, then the limit as x approaches 0 of this guy in between will have to be equal to that value. So if we try direct substitution here, cosine of 0, that will be 1. And the limit as x approaches 1, so this is just a constant function 1, so that any constant will just be equal to the limit. So that will be equal to 1. So then since these are both the same limit, both functions on the end, then that means that by the squeeze theorem, the limit of the function squeezed between them as x approaches 0 of sine x over x is indeed equal to 1, not 0, because both of these are equal to 1. Okay, so these, we'll come back to another squeeze theorem example here, but these trigonometric limits that we saw up here, these are special ones. These two are this one we just proved, and this is another one that's similar for cosine. And then here you can just flip it upside down and that gives the same thing. Or here, if you change the subtraction, it's still the same limit. These can be used to evaluate other limits, and technically could be something to be asked on the AP test. So we are going to talk about that next. Here with these examples. Okay. So if we take the limit as x approaches 0 of tangent, we definitely, if we try direct substitution, we're going to get tangent of 0 is 0 over 0. Now this we can't manipulate or anything, so we're going to have to try to figure out what's going on here. So if we take the limit as x approaches 0, the one thing we know about tangent is that it's sine of x over cosine of x. So maybe start there. And then this is divided by x, but let's make that the same thing as multiplying by 1 over x. And now what we see here is that we see this sine of x over x kind of there. So I'm just going to rearrange, which is totally legal because it's multiplication, this into sine of x over x times 1 over cosine of x. And now we know that this limit right here is equal to 1. That was one of our special trig limits. So we know that the limit as x approaches 0 of sine of x over x, we know that one, that's 1. And then if we do the limit as x approaches 0 of 1 over cosine of x, and we can evaluate that, then we have our answer. So this will be equal to 1. And then we can try direct substitution with this one. It'll be 1 over cosine of 0, which is 1. So this will be just 1. So here, this limit is equal to 1. So we were using this special trig limit to get there. Now this one, example 2 here, this one looks similar, but it's not just x in here, it's 4x. So if we want this limit to equal 1, this would also have to be a 4x. So it's really close to that special limit, the limit as that we know from above. It's just that these have to be the same, and right now they're not. But we can make them the same pretty easily. So if we take the limit as x approaches 0, and we want to put a 4 in the denominator, that's fine as long as we multiply the top by 4. So now we can write this as 4, the limit, because you can always pull out constants, sine of 4x over 4. And now we know that that limit, oops, forgot my x, will indeed be equal to 1. So we already know that. So then this will be 4 times 1. So again, using that special limit right here. All right, and one more example here of these special limits. If we take the limit as x approaches 0 here, this looks really, really similar to that one on the other page here that says the limit as x approaches 0 of 1 minus cosine x over x is equal to 0. Okay, that was one of the special trig limits. This looks a lot like that, but it's 1 minus cosine squared. So what we can do here is this really is a difference of squares. So we can factor this. But really this is the same thing as the limit as x approaches 0 of 1 minus cosine x over x times 1 plus cosine x over 1. If we multiply those together, we get the same thing. Now this limit, we already know, is equal to 0. So we can separate this. And do the limit separately. So we know that this first limit is equal to 0, and then if we try direct substitution here, we'll get 1 plus cosine of 0, which cosine of 0 is 1. So then we'll get 0 times 2, which is 0. So this limit is equal to 0, using this special limit right here. All right, let's do one more squeeze theorem example here. So we have this function here, f of x, and we want to show that the limit as x approaches 0 of this function is equal to 0. That's what this asks us to do using the squeeze theorem. So here we don't have an inequality to start with, so we're going to have to create our own. But the nice thing is that whenever cosine is involved, we always know that it is bound between -1 and 1, as long as you only change the inside. Cosine, as long as you don't multiply by anything on the outside, no matter how you change the inside, it will always be between -1 and 1. Same thing with sine. So now we have an equality to start with. And what our goal is if we have to create our inequalities, we want our whole function that we're trying to find to be the middle function, right? But right now, we're missing this x squared. We don't have that. But we can just go ahead and put it in there as long as we multiply all sides of the inequality by x squared. Oops, sorry, this one up here is supposed to be a positive one. My bad. And as long as we don't multiply by a negative, which if you multiplied by a negative, you'd have to flip the signs, then you're allowed to do that with an inequality. So now we have negative x squared is less than or equal to x squared cosine of 10 pi x. And so now that we have an inequality, if we take the limit of the outside functions and they're both the same value, then the limit of our inside function will be the same value. So let's take the limit as x approaches 0 of negative x squared. With direct substitution, that'll be 0. And the limit as x approaches 0 of x squared. With direct substitution, that will be 0. So then by the squeeze theorem, that means that the limit as x approaches 0 of our inside function is indeed 0. And just so you can kind of see what's happening here, I'll draw you a picture. So here, if we have our positive x squared, that's a parabola, and our negative x squared, that's a parabola. And then if you were to draw the graph of this f of x function, you would see that it goes like this. And it's stuck between these two functions the whole time. And so we can see that the limit here of the x squared and negative x squared are both 0, right? And so since that function is stuck between there, then that function also has to be equal to 0, that limit.